Welcome back to this video lecture. Today I will go through particle wave duality and the double slit experiment. So let's begin with waves. So a common characteristic for waves are that they interfere with each other. So if we conduct an experiment called a double slit experiment and we use photons or light. So the double slit experiment, I've gone through this twice on this channel already, is simply when you have a wall with two doors, two slits in between. And on the other hand, on the back over here, you have a detection screen. So here you have a photon cannon, a light cannon, a laser beam or whatever. Something that distributes light. So when you have the wave that comes and travels like this is the light wave. It will come to the point where it has to break up into two new waves due to these slits. So you will have one wave right here. And similarly, on the opposite side, you'll have the same thing. So as you can see, these waves, they overlap. And that creates interference. So if two high points of a wave meet, they conduct and create a bigger high point. It's called creation. And if the two low points meet, they will annihilate each other and create destructive interference. So it's constructive and destructive interference. So this will give you an interference pattern on something like this. We have a lot of hits right there, not so much here. So in these points you have very few hits, and here you have a lot of it because the waves, they interfere with each other. So this is a common characteristic for a wave. So if you do the same experiment, exactly the same setup, you have two doors or two slits like this. You have a detection screen right here. And you conduct the same experiment, but instead of light, we decide to use electrons. You will find something fun. So this is light, photons, and this is an electro cannon. When we shoot electrons on this on these slits, you will find something very interesting. You will get interference. So some electrons hit here, not so many hit here, a bit more hit here, not so many here, a few more hit here, a lot of electrons hit this point right here, not so many here, fewer here, and none here. So as you can see, you get the same type of interference as you did last time. So how did this happen? If you only fire one electron at a time, this is the pattern that will build up. It's almost like the electron is interfering with itself, like it's traveling back in time and forth in time and know somehow about the other electrons. So this baffled scientists and myself for a very, very long time. So we start by asking the question, which slit did the electron go through? This one or this one? It's pretty straightforward to find a solution. You simply just block off one of the slits. So let's do that experiment as well. Let me just adjust this camera. So we have to take the same experiment right here. But now one of the slits are blocked out. And we put the same detection screen right here. And now when we fire the electrons, you will find a pattern that looks like this. No interference. Just as you were to throw baseballs through a door. So how did this happen? The electron interfered with itself because it has wave-like properties. And this is the core idea, the fundamental idea of, well, wave-particle duality and quantum mechanics in general. So we want more information from this experiment. So let's try to conduct this experiment slightly different. So let's do the same experiment here, the double slit experiment. We have 2 slits and a detection screen right over here, and here we have the famous electron cannon that shoots out 1 electron at a time. And let's say, for example, that these slits are thousands and millions of miles apart. There's no way that the electron can know about another electron in the future. So you fire 1 electron at a time. That's the rule. So over time, as we saw previously, you will find this interference pattern. So where this experiment becomes even more wicked and weird is when you try to observe it. So let's, for example, say right here, I have a light beam. That's a light beam. And I will send out very, very low intensity light to try to measure the electron. So you put out the electron, it goes through here. This is the electron. And then you will shine a little beam of light, and you will get a reflection. And that reflection is how you measure the position of the electron. So by putting an observer, something that can measure the electron, well, then you can decide if it went through this or this slit and try to see how the interference effect works. Maybe the electron splits up into 2 pieces and go through both and interfere with itself or whatever. So we tried this, and it seems pretty straightforward, but this does not work. Because you see, light can have an intensity. How much light, the amount of light beams or photons that comes out, that leaves this apparatus at a given time. That's the intensity. But the intensity do not alter with the energy. It alters with the total energy, but not with the energy of a single photon. Because the energy of a photon, or the momentum of a photon, the energy of a photon is simply h multiplied by the frequency of the light. Now we'll get into greater detail about this in just a second. So by increasing the frequency, you get higher energy, right? And we also know that momentum is equals mass times velocity, but that does not really work in light. So how you get the momentum of a photon is quite different, and I will explain that soon. So let's go to this formula again. That energy is directly proportional to the frequency of light. So the only way to make light weaker is to make the wavelength bigger. And herein lies the problem, because most light has a wavelength of about 10 to the minus 5 meters. Where an electron has an diameter of 10 to the minus 18 meters, I think. So you need to make the wavelength so much smaller, and by doing so you will increase the energy. And when you increase the energy, you will simply just knock this electron out of place when you try to measure it. So if you want a wavelength, a beam of light that is weak enough to not disturb the electron, it will maybe look like this. And how on Earth is this wavelength supposed to measure this electron? That won't happen. So as we see in the experiment, if you have a wavelength that is accurate enough to distinguish the distance between this slit and this slit, the momentum that beam of light will carry will exactly wipe out any interference from the electron. And that is the observer effect. So what we can conclude from these experiments is that electrons can behave like waves. So can waves behave like particles? Let's look into more depth about that. So let's take a piece of metal. This is my piece of metal. It's beautiful, beautiful, right? And I decide to shine a beam of light on it. And as I do so, I start to notice something very weird. Electrons start to leave the metal. So this is my beam of light. And by shining that light on my piece of metal, I see that electrons leave. So this is called the photoelectric effect. And it was described and pretty much solved by Albert Einstein, and he actually won a Nobel Prize for doing so. So if you plot the kinetic energy and frequency on a graph, it will look like this. So this is the kinetic energy, the energy that the electron have after leaving the metal. And this is the frequency. So you will only get electrons to leave if you have a frequency, a certain frequency. And after that it is just linear. And this is the threshold frequency, F0. And since this is a straight line, you can conclude that the kinetic energy is simply a constant h multiplied by the frequency minus phi, which is another constant. And here is phi divided by h. And h, that's Planck's constant. That's the line. So now if the kinetic energy is 0, that means that hf will equal phi. And when that happens, phi is simply hf0. So the gradient of the line is h, which is, as I mentioned before, Planck's constant, which is simply 6 times 6.63 times 10 to the minus 34 joule seconds. So not joule per second, strictly joule seconds. So this is slightly weird, right? How can just beams of light give kinetic energy to electron? Well, it was described by Einstein as light comes in chunks of Planck's constant. So the energy of light, as I said before, is Planck's constant multiplied by the frequency. But for this to actually work, you need momentum on the light. And since the formula for momentum is simply P momentum times equals mass times velocity, that doesn't really work because a photon, Einstein's photons do not have any mass. So we also have this very famous equation, E equals mc squared, which if you derive that in another way, you will find that m equals E over c squared. And if you put this new energy term in, you will find that P equals E over c squared multiplied by c, which is simply E over c. And we know that the energy for photon is hf. So now you can derive this even further and say P equals hf divided by c, which of course equals h over lambda. So you know that P equals h of lambda. So momentum is directly proportional to the wavelength of a particle. So now we can start to see as a bunch of things that waveless particles can have momentum, which was quite new. And they can, massless particles can have momentum. And that is pretty interesting. So how does this apply on, let's say, electrons? So in 1972, Davidson and Germer, very famous physicist, tried the double slit experiment but with electrons. But instead of a double slit, they used a crystal, where the holes in the crystals between the atoms worked as the slits. So this is the crystal. So we shined light through this electrons through this crystal, and what you found was, as I said earlier, yet again interference. So this is the detection screen. You found some electrons here, not any there, some here, and some here, and so forth. So you got interference yet again. And as we said before, lambda equals h over p, which simply then is h over mv, since p equals mv. So this would be interpreted as electrons, or anything really with mass, could have a wavelength. So if that is true, the energy for an electron in an electric field is simply Ne equals the charge q multiplied by the velocity. And that is EV. I mean a volt, not velocity. EV. What I mean by that is, if you have two plates, one positive and one negative, and you put an electron in here, that electron will be attracted to the positive plate with that force. And we know that an electron has a charge of 1.6 times 10 to the minus 19 coulombs, or a half mv squared, which is the kinetic energy. So we know that these terms should then equal. So EV is equal to 1 over mv squared, which you can derive as v squared is equal to 2 electrovolts divided by m. And remember, this is volt and this is velocity. Do not confuse them. I know it's confusing, but that is how we write things. I'm sorry about that. Which then essentially is just v equals 2ev divided by m, the square root out of that. So as I said before, the wavelength is h over mv. So this should then simply be lambda. We have a new velocity term, is then h over mv, and that is h over 2mev, the square root of that. So as you can see, electrons can have a wavelength, and that is the fundamental core of wave-particle duality. Thank you for watching. Hope to see you in a future video.